So our last topic for this course is computation. And so we're going to hit on a lot of different things that, as we were just talking, each one of these things is its own course in and of itself. So we're only going to give you a broad breadth introduction to these things. But we're going to motivate it from a practical perspective. Computational models. Exactly what is computation? What is a computer? What is an algorithm? The limits of computation. Yesterday I asked a philosophical question, can computers solve any problem? And in fact the answer is no. The computers or algorithms can't even decide very, very practical problems, right? Some very other problems that, everything that you've written a program for, those are problems that can be solved by a computer. But there are some questions that cannot be solved by a computer or an algorithm. Then we'll get into a little bit of complexity, P versus NP, and complexity classes. Pretty much everything that you've done up till this point, except for those brute force algorithms, those are all polynomial time algorithms. And that defines a class called P. Some of the other, which stands for deterministic polynomial time. There are, of course, hundreds of other complexity classes that you can define, that have been defined that capture some notion of computational resources. Then we'll also look at reductions, because this is how, within complexity, you quantify that this problem is at least as hard as this problem, right? That if you can solve this problem, then you can definitely solve this problem, right? Again, our motivation is going to be what is computation and what is computable, okay? Here's the same question that I asked last time, except in a little bit of, it's not a question anymore, it's a statement now. Algorithms solve problems. Or you can substitute this for computers, because you can think of computers as being algorithms. However, algorithms are thousands of years old, right? Computers are only dozens of years old, right? 60 years, whatever you want to say, right? Modern computers at least. So algorithms have existed for a lot longer than modern computers. Computers just run algorithms. Algorithm is basically a specification for some process, right? The problem here is that this is a dictionary definition. If you pulled out your Webster's, you could look up what an algorithm is, and there would be a very Webster-y dictionary definition for it that said a process, a specification for executing a process, right? Solve, what does it mean to solve a problem? And what are problems, right? The problem, I mean, every day we have a problem. Oh, I forgot my umbrella and it's raining. That's a problem, right? But in the context of computation, what are problems? What are each one of these things? I'm going to translate this to something that is less of a dictionary definition and something that can actually be captured mathematically, right? Turing machines decide languages. All right? Now, there are three components to this: Turing machines, deciding, and languages. And we're going to have to establish quite a bit of foundation to even get to what these definitions are, okay? But this is called the Church-Turing Thesis. Now, it's a thesis, that is, it's a proposition. It's not something that is mathematically provable. This is a mathematical statement, and you can define it this way, but whether or not you accept that Turing machines are what we mean by algorithms, that's your choice, right? It's basically, these things are incomparable, because this is a dictionary definition, and this is a mathematical definition. There are equivalent mathematical definitions of what a Turing machine is. For example, lambda calculus. That's why we call it Church-Turing Thesis. I think Church was responsible for lambda calculus. But in any case, what you can do is you can come up with a different mathematical model with a different but just as rigorous mathematical definition for what it means, what you mean by an algorithm. And then you can show that it is more powerful, less powerful, or just equivalent to Turing machines. You probably come up with it's less powerful or just equivalent to Turing machines. And you can, then you can come up with a different definition for what it means for an algorithm to solve problems. Those two definitions can be proven to have some mathematical relationship. But it's still a thesis on whether or not you think that these two statements are equivalent. The vast majority of people accept that this is what we mean by algorithms, that by problems we mean languages, and by solving we mean deciding. Okay? So that's why it's a thesis. It's not a theorem, right? It's not because you can't resolve a dictionary definition to a mathematical definition. They're completely different languages. So what we're going to do is we're going to go through each one of these things, and I'm going to establish what each one of them means. We're first going to look at what it means to say that you've got a language. Okay? So a language definition, or definitions, I guess. An alphabet. We need in order to have a language, you need words, and in order to have words, you need letters. So an alphabet, and we usually use sigma to denote this, is a finite set of symbols. The English alphabet is, of course, of size 26. There are 26 letters. Other languages have, thousands. Chinese, Japanese, Korean fonts. They have thousands of characters in their alphabet, right? Cyrillic fonts and the ASCII text table. Mathematics has its own set of symbols. Or if you just want to look at arithmetic, you've got 0 through 9, plus, minus, multiplication, all that stuff. Those are also symbols. That defines an alphabet for that language. Right? A string is a finite sequence / combination of symbols from sigma. Okay? Now to understand this, I'm just going to go ahead and establish that what do we mean by sigma? Well, we're computer scientists, so let's just suppose that it suffices to consider sigma being the set 0 and 1. Why? Why is it enough to have only 2 symbols? English has 26. Chinese has 10,000 characters or something like that, right? Japanese has 46 hiragana characters, and then 46 copies for katakana, and then thousands more kanji characters, right? So we've got an entire alphabet. Why is it sufficient to only consider 0 and 1? Do we really realize the English alphabet using A, B, C, D? How do we do it in computers? We do? What is A in a computer? Lowercase a. So I think it's 95, right? No, uppercase A is 65, right? So lowercase a would be, I forget, 92 or something like that, right? Why is it justification for this? Any alphabet can be encoded with 0, 1. You all did this, right? What's my proof of this? You all successfully, hopefully, implemented Huffman coding, right? Another example would be the ASCII text table. That's what I was getting at, right? Or Unicode. Any language that humans and some non-humans can come up with, well, actually, wait, I forget. No, they rejected Klingon from the Unicode, didn't they? I think that they did. But they still have ancient Egyptian hieroglyphics encoded with Unicode. So you can actually write in ancient Egyptian hieroglyphics if you want to on a computer, right? So it's enough to consider, 0 and 1. And it makes sense because that's all a computer understands. If you have any piece of data, you can always encode it as a 0 or 1, right? So that is our alphabet. And our string, and so a string, as an example, for example, we've got 0 or 1. Those are strings. Give me some more strings. Give me some more binary strings. 0, 0, right? 0, 1. 1, 0, 1, 1. These are all strings of length 2. These are all strings of length 1, right? What would be the first lexicographically? String of length 3, 0, 0, 0, 0, 0, 1, dot, 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 right? You can take any word, or sometimes we call these words, right? Or strings of any length, and binary, we do allow, leading zeros here, and you can form a word out of it as long as it's finite. Right? You can consider infinite strings that go on forever, but we're not going to do that here. Well, if these are strings of length 3, 4, 5, etc., all going on that way, 2 and 1, what does a string of length 0 look like? We use a special symbol for that. Right? This is the empty string. It's a string of length 0. Hopefully this sounds familiar, because this is exactly what you do when you program strings. Right? You can have a string of length 0, right, in most programming languages. You can have, there's another special string that's used in programming languages, some programming languages, null, right, no string. These two are not necessarily the same thing, depends on the language, or none, right, if you're in Python, etc. Right? So there are special things with respect to programming languages. Forget about it, we're only going to use lambda here. Okay? Lambda is going to be our empty string. By the way, sometimes, alternatively, sometimes authors use epsilon for the empty string. I'm going to go ahead and use lambda. All right? So, the set of all binary strings over 0, 1 is denoted as sigma star. This is a set that contains all of those that I was just writing out. 0, 0, 0, 1, dot, dot, dot. Right? It's an infinite set. Right? It contains every possible finite string. Okay? Including the string of length 0, the empty string. Okay? The star operator, or it's called the clean star. I think that's how you spell his name. It means that 0 or more combinations of sigma, of symbols from sigma. Right? And maybe this looks familiar. Have you ever seen the star operator in programming? Oh, what? Give me an example. Wildcards. They match anything, including what? Nothing. Right? Where else? Say, I don't know, period star. Does that look familiar? Right. This is any character. This is 0 or more occurrences. Right? That's the clean star right there, the star operator. What is this? This is a regular expression. And by the end of today, maybe, we'll understand why it's called a regular expression. Right? What does regular mean, right? Does anybody else have another? Here's a common one. I think maybe B. It really depends on the language. Right. What would that be? That's a special character there. I think in some languages, in some regular languages, this is going to be any white space character. Some languages use W, I think, right? So this is 0 or more occurrences of a white space character, right? This would be 1 or more occurrences, right? Well, how do we get 2 or more occurrences? 2 white space characters, and then you can go ahead and put a clean star on this. This will be any number of even white space characters. Right? So you can do irregular expressions like this. And by the way, the syntax is not 100% right here. That's because there are lots of ways that you can do regular expressions. You can do GNU regular expressions using grep, GNU regular expressions. There's Perl compatible regular expressions. PCRE, Perl compatible regular expressions used in a programming language like PHP or Perl, right? This would be from the command line. And you've got a few other established, regular language syntax families out there, right? But extremely useful because you can write a regular expression to, say, match every telephone number on a web page, so that you don't have to go through and have a program manually pull out what you think is a number and then verify that it's a number. You can have a regular expression to match emails. You can have a regular expression to match the end-line character and then replace it with 2 end-line characters to automatically double space everything, right? So find and replace regular expressions, extremely useful. We're going to use them in the context of theory and to establish languages, right? So now that we have that foundation, what is a language? Definition. A language is a set L, which is some subset of sigma star, right? In other words, it is simply a set. It could be finite or infinite of strings over sigma. And of course, again, we're going to restrict our attention here to 0 and 1. That's it. There's nothing special there. It's some subset of all of these strings. Now, why does that help us with this problem right here? Turing machines decide languages. Okay? So, fact. Any problem can be encoded as a language. Right? Any problem. It doesn't matter what the problem is. It doesn't matter that the problem is about graphs. It doesn't matter that the problem is about numbers. It doesn't matter that the problem is about some geological survey data that you want to process. It doesn't matter if it's part of weather data that you're trying to find data anomalies in, like you did in the first part of this class. Right? I'm going to show you how. Right? So let's take a problem that we've been working on several times now, dealing with, say, graphs. Right? Let G be a graph, and let X and Y be vertices in G. And our question, our problem, this is the problem, is does there exist a path from X to Y? Right? Seemingly there's no math here at all, except for, of course, the mathematical definition of a graph, that it's a set of vertices and it's a set of unordered pairs of vertices called edges. Okay? But this is our problem. How can we encode this problem? Let me go ahead and take an instance. All right? Here's a graph. A, B, C, and D. Right? That's my drawing of this thing. How would you actually represent this, say, in a computer? You would end up, say, with an adjacency list, a matrix, right? You would say that you'd have 0, A does not go to B. It does go to these things over here. B goes to only D, right? C goes to A and D, but not to B. I've written it too chunky. and D goes to all three of them, but not to itself. There we go. What does that look like to you? Bunch of zeros and ones to me, right? So what you could do is you could encode. G is going to be an encoding of n, an adjacency list, or matrix say. Right? And so what you could look at is, and we use Langle-Wrangle on these, this is going to be is on encoding of some graph, G. And all it would be is maybe you have a list of those vertices. So 0, 0, 0, 1, 1, 0, 1, 1. So maybe here's your list of vertices, 0, 0, 0, 1, 1, 0, and 1, 1, followed by a semicolon. And then this adjacency list here, or matrix here, 0, 1, 1, 0, 0, 0, 1, dot, 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 right? That's your encoding. But wait a second, we don't have these symbols in our alphabet. That's okay. If you have 4 symbols, guess what you can do? You can run Huffman coding. And now you've cut it back down to 2 symbols. Right? I'm just doing this for our readability. A computer would have no problem with this. We wouldn't even need to know these demarcation points here, as long as you had a way of having the computer parse this out. Right? So this is going to be an encoding of some graph. In other words, Langle-Wrangle G is a string over sigma. Right? Well, if we can do that with a graph, we can certainly do that with 2 vertices. Right? At the end of this, put another special symbol, and then x would be, I don't know, say that we are asking a question about A and B, so x would be 0, 0, and say that we're asking a question about, can I go from A to B over here? 1, 0. Right? So you can also encode those. So you could encode a graph along with, say, 2 vertices. Encode that entire thing. This is simply a binary string. Right? You've been doing this over and over again for the last year in CS1 and CS2 and now in CS3. You just didn't think about it because you let the computer do it for you. You write high-level code. Your graphs are actually text files with 0, 1, and 3.5 for the weight for the actual graph, right? But under the hood, that is encoded in ASCII. It's all just a bunch of zeros and ones. Right? Your programs are compiled to machine code, which is nothing more than a bunch of zeros and ones. Your high-level code, C, Java, Python, whatever, it's still just a bunch of zeros and ones, even though you can read it because of the ASCII text table. So everything is just a binary string. So what is a language? I'll define L to be all encodings of a graph along with 2 vertices, such that G is a graph, and there exists a path x to y. Once I've defined that language, this is nothing more than a set of strings. Some strings are in this set, some strings are not in this set. For example, if I've got x and y, like I did before, if I encode this graph as g, x, y, then we say that this is in the language. Right? It's in the language because a path x to y exists. Here's another graph, x, y, and it looks something like this. Same number of vertices, but there's no edge there. It's isolated. Right? This is another encoding. I'll call it G prime, x and y. Again, it's just a bit string, and it is not in the language. Right? All I've done here is define this infinite language of all the binary strings that represent an encoding of a graph and 2 vertices, such that there is a path from x to y. Right? Well, what about the other language? Right? This is the set complement. If I define L to be this, then this is going to be defined as all encodings of G, X, and Y such that G is a graph and there is no path X to Y. Right? That's the complement language. Now, careful, there is a technicality here that I'm assuming that these are all correct encodings. That this is a valid encoding, this is a valid encoding. Just some random binary string, that might not actually correspond to a real graph, or it might just be garbage, right? For example, the empty string, well, that could be the empty graph. But if you've got an invalid string, say it's a graph that encodes a multigraph instead, right? Then we would say that that's in neither language, and that's just a small technicality. Okay, so because if you're strict about it and you define this language as this thing, well then all invalid codings would also be in the complement language. Right? So what I've done is I've transferred the problem, answering the question, does there exist a path X to Y in G. I've changed it. I've changed it such that if you take the encoding of these things, is this in the language L? Right. So hopefully I've justified to you why languages, that it suffices to consider this model of computation. Because all you have to do is take whatever you're talking about. It may not even be a graph. It could just be a number. Here's a number. Well, what's an encoding of a number? It's the binary representation of that number. And now your question is it prime or is it composite? That defines two sets, a set of all prime numbers and a set of all composite numbers. Is it in this one or is it in this one? Right? And so the question is simply just testing whether or not a string is in a set of strings or not. Okay? And that's kind of what it means to decide a language. Right? Definition. A computational, what do I want to call it? A computational item? I'll say model for now. Decides a language if for any input X, and now we're saying that X is a binary string, right? Remember that this is the set of all binary strings, so X definitely has to be in it. It is a binary string. It eventually ends its computation and answers yes or no, right? Period. Okay? That's what we mean by some computational thing, and we're not going to look at Turing machines until maybe tomorrow. That's what we mean that it decides a language. There are actually two things here. A computational model, an algorithm, decides a language if it eventually ends. In other words, it halts. Right? You can't have an algorithm that, given this element, goes off on an infinite loop, right? Or will never reach the end of its computation cycle given infinite time. Right? If that happens, then it doesn't decide that language because it never answers yes or no definitively. Right? Yes or no answers, they correspond to decision problems. Questions like I just asked, given a graph G and two vertices X and Y, is there a path or not? Right? So the decision version that we just looked at was G, X, Y. Does there exist a path X to Y? Yes or no? This is a decision version. Decision. Okay? You're just trying to answer yes or no. We've seen other types of problems, right? And I've hinted at this before, and now it's come up. What about optimization problems? I don't want to know is there a path or not. I want to know is there a shortest path, right? So here's another question. Given g, x, and y, what is the length of the shortest path, x to y? This is an even more general question. Why? What if you had the answer to this? What if the answer was 5? What would your answer to this up here be? The answer would be yes. When you ran Floyd-Varshall's algorithm and you found that there was no path connecting x and y, what was the length of the path? What placeholder did you guys use? In Python, say. Math.inf. So if the answer was int, would you have your answer up here? Yeah, the answer would be no, there is no path. Right? So this is an optimization version. I want to justify to you further that any problem, including an optimization problem, can be translated to a language. Okay? Let me go ahead and encode this. I'm going to encode this as g, x, and y, and k. This is going to be an encoding of a graph, g, vertices, x and y, and an integer, k. And I'm going to change my question. Not what is the length of the shortest path. My question is going to be, is there a path of length k or less or greater, or I'm just going to go ahead and go with exact here, connecting x to y. What I've done is I've taken this optimization problem of what's the shortest path, and I've changed it into a decision problem. What's an answer here? An encoding of a graph G, vertices x and y, and is there a path of length k connecting x to y? The answer here is yes or no. You can ask this question with different encodings. Does there exist a path of length 1? Does there exist a path of length 2? Does there exist a path of length 3? And eventually, you'll get an answer of yes. In which case you have an answer to this question up here, and you also have an answer to this question up here. Right? The longest path, of course, would be n minus 1, and so if you get a no, 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 all the way up to that, then you're assured that you don't have to go any further. You don't have to test, is there a path of length 1 billion on a graph of 5 vertices? If the answer was no for 4, it's certainly going to be no for 4 billion. Right? So you can take an optimization problem and you can translate it into a decision problem. What's another type of problem? Right? What did you actually have to do on your homework 3? You not only had to report what the length of the shortest path was, you also had to report what the actual path was. That's called a functional version. Given graph g, x, and y, output the shortest path, p connecting x to y. Okay? What's the answer there? The answer is no longer a yes or no. It's no longer just a single number. What is it? How did you do it in Python? Nobody did it in Python? How did you report? Certainly you wrote a function, give me the shortest path x to y or something similar. What was your return type on that function? A list of vertices, right? That's what I did, right? I did, by the way, do another solution because there were still some complaints about the consistency on the formatting. I don't think any of the graphs, any of the answers were wrong in the grader. I think that but I do think that the formatting was inconsistent. So last night I just wrote up, actually I wrote up 2 solutions, and then I reran all of them and made sure that they all had the same formatting. Including in the grader, if you want to look now, it reports whether or not it's a spanning tree or a spanning forest. Right? So what would the answer be here? The answer would be a sequence of vertices. X, V1, V2, dot, 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 all the way up to Y. Right? Where maybe there's already an edge here and that's the shortest path, it would still have X and Y as your endpoints. Right? So it's a sequence of vertices. Well, guess what? If you have a sequence of vertices, what can you do? You can encode them. X, V1, V2, dot, 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 Y. Right? You can encode them as a binary string, because that's what they were in Python when you returned it. At the end of the day, under the hood, everything is just a bunch of binary sequences. Right? So how can I change this functional version into a decision version? Right? I can ask a different question. I can, let's see, what did I do? Right, yeah, here's the functional, so taking a functional version into a decision version, you can encode the graph, X and Y and Z and I. And this is an encoding of G, X, and Y, and Z are vertices. Of course, G is still a graph. And I is an integer. And the question now becomes, in the shortest path, X to Y, is the ith vertex Z? And now it's a yes or no question, right? In fact, there are games like this, like 20 questions, right? You can't ask like what color is it, right? But you can ask, well, is it red? Is it blue? Right? Yes or no questions. Same thing with computation. You're not allowed to ask these kind of questions when you're looking at the nitty-gritty theory. You're only allowed to ask decision versions. Well, is the first vertex V1? Yes. Is the second vertex V2? Yes. Is the third vertex V3? And you can actually build the path by just asking yes or no questions. Because if you ever get the answer of no, well, okay, then it must be some other vertex. Go ahead and ask that vertex. Is this the ith vertex? Is this the ith vertex? No, 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 until you actually get a yes answer. And of course, if you get all no's, then you know that there's no path. And so you know the original answer to the original question of no, there is no path. Right? All of these things are interrelated. It doesn't matter if you have an optimization problem, a functional problem, or what. Right? Any function can, or any problem can be encoded as simply just a language. Right? And is it in the language or is it not in the language? Okay? Now, we're not going to get to Turing machines today, but we are going to start with a very simple computational model called finite state automata. Or FSA, or automatons, right? Automata is just the plural form. So what is an automaton? It's kind of an old word that was used a lot in the 50s. Automaton just meant robot back in the day. An automaton is just something that, you start it and it only does what it's programmed to do. It just goes off and starts walking. If you program your robot to go around in a circle, that's all it will ever do, right? So in other words, it's going to be a very limited, very simple, very limited computational model. Right? You might have thought that, well, computers are all there is. And computers are dumb, right? They're very simple from a certain point of view. They can only do exactly what they're told. Right? This is why they're very difficult to program, because you have to use a very literal language. You can't be figurative about anything. You can't say, if the temperature is too high, go ahead and sound an alarm, right? What do you mean by too high? Right? And how do I sound the alarm? You can't use that high-level English, right? You have to go down to the nitty-gritty of actual programming languages because computers are dumb, right? So I'm going to go ahead and give you the definition, and then we'll understand it better with pictures here. So a finite state automaton is a 5-tuple. It consists of Q, a set of states, right? Alpha, or sigma, sorry, our alphabet. And again, we're just going to go with 0 and 1, just to keep things simple. Delta, which is a transition function. There we go. This is the Cartesian product. So given the current state, which is this thing right here, and the current input bit, which is this thing right here, transition to a new state. It could possibly be the same state, but we'll interpret it as a new state no matter what. Right? So given the current state that you're in, we're going to read the next bit of the input, and then we're going to transition to another state. Right? And then the other two are just going to be simply Q naught is on initial state. You got to start somewhere. And okay. And F is a subset of our states are accept states. All others are reject states. Right? That's the formal definition. Okay? Here's the intuition. The finite state automaton will read the input bit by bit. But it will only read it. There's no output. No output. It's read only. It cannot re-examine input. In other words, it's one way. It reads the first bit, then it reads the second bit, then it reads the third bit until it gets to the end, right? And at the end, at the end of the input, it stops in some state. Right? There we go. And I'm going to have to go to the next one. It's going to stop in either an accept state. This means that the input, and I'll label it as X, is in the language. The input is in the language L defined by the finite state automaton. And or it'll be in a reject state. The input X is not in the language L. Right? And cut and paste that, and it's just the complement. Okay? So again, pictures are a lot better. Let me draw a picture instead. Let me draw a picture of states. This is Q naught. Here's another state, Q1. Here's another state, Q2. And to denote the rejecting states and the accepting states, we draw another circle around this one. This is the double circle is an accept state. Right? This, of course, Q naught is the initial state. That's where we start. And then you can draw transitions between all of these states. For example, if our input is a 1, if we're in this state and our input is a 1, we'll stay in this state. The only other possibility is that the input is 0, and so if it's a 0, we'll go ahead and go out, say. All right. Say that we're in this state, and if we see a 0, I'll go ahead and stay in that state. If we see a 1, I'll go ahead and go over to this state. If we see this, if we're in this state, then I see a 0, say, I'll go ahead and go back to that state. If I see a 1, I'll go ahead and go back to this state, 1. There we go. Now, I'm not sure what this, what language this finite state automaton defines, but we're going to go ahead and test a few things. All right? So let's go ahead and look at the strings, at some strings. What about, say, 0, 1, 0, 1? Is it in or not? Okay. Here's the way that you compute with a finite state automaton. You always start out in the initial state. I'm looking at the input now. The input is 0, so what state do I transition to? Q1. Then I go on to the next input, next bit in the input. I see a 1, so we'll go over to this state. Now, if we were ended right now, if we ended the computation right now, we would end in an accept state and accept it, but we're not done yet. We have to read all the way to the end of the input. 0, I go back to this input, or to this state over here. 1, I go back to this state over here. So is it in the language or not? We're in an accept state, so yes. Remember, yes or no questions. Is it in the language or not in the language? Okay? Well, 1, 0, 0, 0. Okay? What's the computation on this input string? 1, 0, 0, 0. Is this an accept state? Nope. So, is it in the language or not? Nope. Okay. Maybe we can start to see a pattern emerge here. Give me another string. Give me your favorite small binary string. 1, 1, 1, maybe? I like that one. I don't know why. 1, 1, 1. Is it in the language or not? Nope, that's not an accept state. That's the only accept state. All right. Okay. What about 1, 1, 1, 1? 1, 1, 1, 1, 1, 1, 1. It's going to be? Nope. Okay. Yep, okay. I've got it now. Well, we said before that if it were shorter, 0, 1, that it would be in the language. And then if we see 0 or 1, we have to jump back, or we have to jump back over here. All right, let's look at some others. 1, 0, 1. 1, 0, 1. Yes, that's in the language. Okay. 1, 1, 0, 1. Is that in the language or not? You tell me, where do I go? So I see a 1. Where do I go? Stay there. Stay there. Now where? Q1. Now where? Q2. I ended up in an accept state, so yes. Do you start to see a pattern emerge? The only way that you could get to this only accept state is by what? By ending with a 0, 1, right? So this language is all strings ending in 0, 1, right? Doesn't seem useful, or does it? Well, maybe. Maybe not this one, but what if I modified this? What if I defined a finite state automaton to accept any string that ended with not a 0, 1, but say a 0? What would that look like? Help me design that thing. So let's go ahead and create an accept state here. And if it ends with a 0, then then I want to be in that state. What if it's 0, 0, 0, 0, 0, 0, and then the last one is 0? I want to stay in that state. On the other hand, if I'm in this accept state and I see a 1, and that's the end of it, I don't want to be in this state because I want to be in a state where it rejects. So I'll go ahead and go save back over here. All right? I've taken care of both of the transitions out of this one. What about this one? What if it's just 1, 1, 1, 1, 1, 1, 1? I want to make sure that I stay in this state. I'll go ahead and make this my initial state. All right? Q0, Q1. All right? That's an even simpler machine. But now it accepts any string that ends with a 0. Is that useful? What can you say about a binary string that ends with a 0? No? 1, 1, 1, 0. What is that? It's 14, right? What about 1, 1, 0? What is that? 6. 1, 0, 1, 0. What is that? 4. Let's go with 1, 0. What is that? 2. 0 is 2. Do you start to see the pattern? I skipped a bunch in here. If something ends in a 0, if a binary string ends in a 0, what is it? It's even, right? This finite state automaton decides even or odd. That's something that you do constantly in programming languages, right? So even with this really simple, stupid model, we can do some reasonably powerful stuff. I can tell you if this is even or odd with just 2 states, right? And looking at the binary representation, okay? We can also do things that are even more powerful, right? For just one more exercise here. Let x be a binary string. Then the parity of x is even, that is 0, if it has an even number of 1s, and it's odd, that is the parity is going to be 1, if it has an odd number of 1s. Right? In fact, that's even more useful than telling whether or not something is even or odd. Have you ever heard of a check bit or a parity bit? Right? So I want to transmit data over a network. I transmit, say, maybe 1K of data. How do I know that one of those bits didn't get flipped in my transmission? So that instead I sent you 500 ones and 500 zeros, right? The parity there is 0. I could send one additional bit that I'll compute the parity of my message, add that bit to the end, send that to you. You can compute the parity, and if our answers don't match, then you know at least that there were an odd number of mistakes sent in the transmission, which is pretty damn powerful. Right? And you can then request that it get resent. This is a very, very useful but very, very simple problem. Right? All right, let's go ahead and design a finite state automaton to decide this language. Right? Given x, we will accept if it has an even number of 1s. Okay? Here's a hint. You only need to start out with 2 states. Now, first of all, we need to take care of the initial state. Should this be an accepting state or not? Now, you might think, oh, I haven't read any input yet. But remember that the empty string is part of potentially part of languages. So the empty string, what's its parity? Is it even or odd? Well, how many ones does it have? 0. And is 0 even or odd? Even. So we would need to accept it. Right? Now, assume that in this state, I've seen an even number of 1s. If I see another 1, then I don't want to accept it. I'll go ahead and jump out into a non-accepting state. Okay? But if I see a 0, well, that doesn't matter. It could be 1, 1, and then a million zeros, and I would still accept it. So I'll stay in that state. What if I'm in this rejecting state over here? In this state, so far, I've seen an odd number of 1s. So if I see another 1, then I want to jump back to the even state. But if I see zeros, well, I still have counted. I'm not counting here, but I've seen an odd number of 1s. Right? So let's verify. Let's test some strings here. 0, 1, 0, 1. What's the parity here? Well, there are 2 1s, so it has an even parity. We should accept it. In or not. So simulate the computation here. 0, 1, 0, stay there. Then 1, we jump back over here. Did we accept it? Yes. What about 1, 1, 1, 0? There we should not accept it because it has an odd number of 1s. So 1, 1, 1, 0 stays in that state. So no, that checks out too because we don't want that string. Okay? If you wanted to flip all this stuff and you want to know if it has an odd parity, then you'd be looking at the complement language. And the complement language, all you have to do is take accept states and reject states and swap them. It's that simple. Okay? So that seems like we can, with this computational model, we can decide some pretty powerful things already. We can do parity, right? We can do even odds, right? We can do any fixed number of divisions, like is it divisible by 4? Is it divisible by 8, right? Because that's just a shift, right? We can get away with that. But what are some other problems? For example, given, say, a number, given, let's look at some practical problems that you might have done before. Given an integer n, compute the sum of I equals 1 up to n of I. Right? So now remember, this is a kind of a functional problem. Given the input, you actually want to output a number or functional problem. It's not really an optimization problem because we're not asking for the best solution. So it's still a functional problem even though the output is a number. Do you think a finite state machine would be able to do this? Well, remember, and you have done this before. Why do I mention it? What is the summation of natural numbers 1 up to n? By now you should have it memorized. N times n plus 1 over 2. This is what? Gauss's formula. Right? So can you compute Gauss's formula with a finite state machine? Now, given the finite state machine can only end in an accept or reject state, so you would have to translate this to a decision version. Right? You would have to translate n into, say, another variable k here. And then you'd have to say, well, given n is the value of the summation equal to k or not. Right? And then this is a yes or no question. Right? Question right here. And so could you define a finite state automaton to do this? Right? In other words, can a finite state automaton count? Right? Nope, it can't. Or let's try to make it do something even more difficult. Given an integer n, is it prime or not? In fact, up until about 20 years ago, nobody even knew if this was decidable in polynomial time. There were only sub-exponential algorithms to do this, but super polynomial. Right? Or even more difficult, given an integer n, what is its prime factorization? That's an even bigger question, right? For example, if I gave you 21, I would expect you to output 3 times 7, right? Factor it out into primes. Right? Each one of these is actually more and more difficult. This is simple, but if even a finite state automaton can't do it. This is even more difficult, but we now, at least in the last 20 years, we know that you can do this in polynomial time. This, hopefully you can never do this in polynomial time. Right? There's no order n to the k algorithm to ever do this, because if you did, well, then you just broke all the encryption that e-commerce is based on, right? Kind of, right? We still have other things that we can rely on, right? But I'm going to give you yet another simple problem that a finite state automaton can't compute. I'm going to define the following language. 0 to the n, and 1 to the n, such that n is an integer. Right. For example, this would include 0, 1. You could argue whether or not it includes the I guess so, a positive integer, right? Then we'll exclude the empty string, because if this is 0 and then 0, then it would be in the empty string. 0, 0, 1, 1. 0, 0, 0, 1, 1, 1. 0, 0, 0, 0. You see the pattern, though, of what I'm trying to get at here. That this is all strings that consist of zeros followed by 1 such that they're the same number of them, right? This is kind of a counting problem. Right? How would you do this in a programming language? For I equals 0, I up to, but not including the string length, right? You'd count up the number of zeros, and then you would switch over. When the first one that you see, you might switch over and start counting up the number of ones, and then you would add those. Then you would see, is this number equal to this number? If not, then output false. If in this sequence of zeros you saw a 1 and then a bunch of zeros, then you'd also say, no, you've got interleaved zeros and 1s. If you see a bunch of zeros and then a bunch of 1s and then a bunch of zeros again, you would say, no, this is not in the language. Anybody could write a program to do this, right? As long as they know some programming languages, right? Of course, I don't know, your grandma couldn't do this unless she knew programming or something, right? And so, you can't, this is an extremely simple problem. But fact, no finite state automaton can decide L, that language L. Right? Why? It requires more computational resources. All right, so give me a computational resource that might help us to solve this thing. Think very simple. You can think of a counter if you want, but think of a data structure. Remember on your first homework, I said that, or I gave you a problem that asked you to show that a queue is more powerful than a stack, because you can simulate a stack with one queue, but you actually need 2 stacks to simulate it. Simulate one. Or what did I just say? You can take a queue and simulate 1 stack, but to simulate a queue, you need 2 stacks. Right? I think I said that correctly. Right? Okay. Well, what if I gave you a stack? Because a stack now seems to be computationally valuable. Right? Here's my algorithm now at a high level here. While you read zeros in X, push a 0 into S. Right? So as long as you see a 0, go ahead and push all those zeros. Let's take this string right here, 0, 0, 0. Once you're done with this loop, while you see 1s, pop a 0 from S. Right? Now, do you accept or reject? If you run out of zeros, or if S still has zeros at the end, then did we have an equal number of zeros and an equal number of ones? Well, I push 3 and I pop 4. Can I do that? No. 3 and 4, is that going to be in the language? Nope. If I push 3 and I only pop 2, that means that I've got 0, 0, 0, 1, 1. Do I accept that string? They're not an equal, right? So then reject. Another condition would be if you still have input. If you had a bunch of zeros, a bunch of ones, and then a bunch of zeros again, you would get out of both of these, and then you'd still have to check the input. If there's still input, then it doesn't conform with this, so reject. I'm able to decide this simple language. I'm not able to decide the simple language with a finite state automaton, but I am able to decide it with a finite state automaton augmented with a stack. Right? And we're not going to get into it, but these are called context-free languages. So regular languages are equivalent to finite state automaton. Context-free languages are synonymous with push-down, that is, stack automaton. All right? Now it turns out if I give you something slightly more powerful, if I give you instead of a stack, if I give you a queue, now you can do any language that a full Turing machine can. Right? We'll talk about what Turing machines are though tomorrow. Right? Context-free languages, these are extremely important. All of these languages are extremely important. Regular languages give you regular expressions. Context-free languages give you language grammars. Has anybody taken 322 already? CSCE 322? All right. In there, you'll learn how programming languages are designed. Maybe. I'm not sure. But in any case, you'll use a tool called Antler. And Antler is a kind of a grammar parser I don't want to get into grammars right here, but you can define a grammar that says there's a grammar for C, there's a grammar for Java. They are basically rules that say what is valid C, what is valid Java. If you've got those are all context-free languages. If you can design a language grammar, then basically you can automate the compilation process. That using this grammar and a lexer or a parser or whatever, you can take this grammar, take your source code and say, it conforms to this grammar, great. Then that means that we can translate it to another language. If we can translate it to another language, that means that we can translate it to machine code. Right? Maybe translate it to assembly, then to a machine code, and then you can actually run it on that system. So context-free languages come up all the time with respect to compilers and compiler research. But there's still yet another, there's a whole hierarchy here. Then there are what are called decidable languages. And that's what we'll look at starting tomorrow. Languages that are decided by a full Turing machine, or TM for short. Right? In fact, it goes beyond that. There are undecidable languages. No Turing machine exists for these. Right? I'm going to prove that they actually exist. And then we're going to look at a very, very practical language. We call them natural languages because they actually do something. Right? Yeah, the first proof I'm going to show you that this is true is a non-constructive proof. We're just going to design some random language and prove that it's not decidable, that there's no Turing machine for it. And then it's Cantor's diagonalization argument. You might have seen that in 235, maybe not, but it's a very, very nice technique. It's diagonalization. And then I'm going to actually design a useful language. That language is not useful at all because we don't even know what that language is or what it does. But then I'll show you that a very useful language called the halting problem something that you can use, say, to statically analyze any program and say that on some input, it's going to result in an infinite loop. So go back and rewrite this thing, right? That would be a very, very useful tool, but that tool does not exist because it's not a decidable language.